Cool. Hi, everybody. I'm Chris. I'm on the SRE team, and I wanted to talk a little bit today about like a brief history of the internet, because we all use it, obviously, to get memes and stuff. But then as I was like writing it, I actually like ended up writing a lot of slides on like TCP, UDP, IP, things like that. So we're going to talk about that too. Also, special thanks to Fars, wherever you're sitting, for that one time where we like drank a lot of beers and just pontificated about computers at happy hour. You kind of inspired this talk, so thanks. so basically, in my job in SRE, like I'm often working on like low-level networking things that like most people don't care about or know about, and even non-technical people kind of like don't even know what the internet is sometimes. They're like, it's that little colorful icon on my desktop. It's like, well, not really, but. I can't not talk about the internet without starting with, Al Gore. No, I'm just kidding. I'm not going to touch that. But we're actually going to talk about another politician, Senator Ted Stevens. If you're on the internet in like 2006, he was in charge of like the overseeing like the net neutrality thing. I don't know. I didn't feel like researching this because we do the same shit like every 10 years where we try to destroy the internet and then don't, whatever. But he had this to say about the internet, which is probably what you actually remember.
The internet, and again, the internet is not something that you just dump something on. It's not a big truck. It's a series of tubes. And if you don't understand, those tubes can be filled, and if they're filled, when you put your message in, it gets in line. It's going to be delayed by anyone that puts into that tube an enormous amount.
So that incoherent rambling is funny to me because he's not like totally wrong, but just mostly wrong. Also, like, it's not a dump truck, but like someone in, at Amazon in 2006 was like, how do I build a dump truck for the internet? So they made S3. And, S3 basically is just, a thing on the internet where we dump memes. Actually hosts 89% of the internet's memes. That's actually a true fact. But what's actually cool about the internet is, we're actually like connecting a bunch of computers together. The best thing about this GIF is it's actually a square image projected on a sphere of the Earth, so it like doesn't work when it turns around. Anyway, but when you're when you're doing stuff on the internet, like preparing for a presentation, you're actually like sending a bunch of traffic like electrically from your computer all the way across the internet to a computer on the other side. And then if you're the asshole from Polar Express, you're going to be like, well, actually, there's Wi-Fi involved, but we're not going to talk about that now. But so I wanted to explain sort of the internet from the beginning, but then I actually found this video. This is Leonard Kleinrock. He was a doctorate at MIT, and he was basically there when the internet began. He helped develop something called packet switching, which we'll talk about in just a second. But I love this video for a few reasons. One, he has like an awesome New York City accent. He was born in Harlem. Two, it gives me like 2 minutes and 36 seconds to get a bite of pizza while y'all watch it. And three, his markers are really squeaky. So without further ado.
So let me describe the events that took place at the time of the birth of the internet. Here at UCLA, we had a time-shared computer, which was a scientific data systems Sigma 7. And it was serving the population of undergraduate and graduate students here as well as the faculty. Just a computer running time sharing in the 60s. When we decided to create this network, the idea was to build a switch which we called an interface message processor. And that was delivered to us on the Labor Day weekend from Boulder Newman back in Cambridge, Massachusetts. It's the size of a refrigerator. It's what we now call a router. That time we called it a packet switch. So it was using and implementing the packet switching technology that I had developed as a graduate student at MIT. So on September 2nd, the day after Labor Day, we connected this switch to our Sigma 7. And bits began to flow immediately. Everybody was there that day, wondering, will it work? And everybody was ready to point the finger at each other if it didn't. Happily, it worked just fine. Next day, we had messages moving back and forth. So this was UCLA. And the time was September 1969. A month later, up in SRI, Stanford Research Institute, another imp arrived in October, and shortly thereafter, they connected their host computer, which was a PDP machine, program data processor machine, a digital equipment machine, to their end. So this is Stanford Research Institute, SRI. The period is October '69. So we decided that we would log on from our machine to their machine. The idea was we'd sit down as if we were a local user on this machine and log on through the network to that machine. Of course, we needed a communications link, and so the first piece of the backbone network ever on the internet was that line from UCLA to SRI.
So actually what he's describing is the beginning of what is ARPANET, which was actually a government-funded project before Al Gore got involved. It stands for the Advanced Research Projects Agency Network. And at its heyday, this was sort of like the main, all of the backbone connections that he talked about. Each one of these circles and squares was either an IMP or a TIP, which is basically like another sort of type of packet routing thing. You can see, and I think if Caitlin's here, Rutgers was on the list. Rutgers, they were sort of, otherwise it's just a bunch of Ivy Leagues, flaunting the fact that they built an IMP. But anyway, so this was the beginning of like packet switching. And you might be thinking like, well, we had phones and stuff back in the 60s, and actually, operators back then were sort of manually packet switching, right? They were connecting copper wires, like depending on where your phone call was going. But what was great about this like new style packet switching is it could actually share like a single communications link, so you could send multiple different types of traffic or connections over the same line. So modern packet switching was invented in the late 60s. It was actually sort of as a declaration from the US Air Force, because they wanted a fault-tolerant communications network for radar data in case like a nuclear disaster destroyed one of the different lines. And then the ARPANET project led to the development of protocols for internetworking, which is basically multiple separate networks joining together to form a big network. So that facilitates this sort of diagram here, where we have a bunch of packets, the original message being in that order. It will start to flow, across the internet and get to the second host. Wow, great hit. And anyway, you might be thinking like, how does it know how to, those have arrived in the wrong order, like how does it know how to like put those back together in the right order? So that's when we start building protocols on top of these things. So TCPIP, which we're still using today, was the transmission control protocol and the internet protocol that were built to facilitate like this new packet switching technology. So the internet protocol suite provides like end-to-end data communications, specifying how data should be packetized, addressed, transmitted, routed, and received. IP is cool because it's like connectionless, so it means that all the data that the packet needs to get to its destination is actually stored on each individual packet. I liken this to kind of like dog tags, right? With like the dog's address and phone number. If you had multiple dogs, you're going to give each dog tag this, the same information. Like a connection protocol would be like if you had 3 dogs and you only gave one dog the tag with the information on it, and the other dogs just kind of only followed those dogs, right? So the link layer, it's broken up. TCP/IP is broken up into 4 different layers. So the link layer contains communication methods for the data over a single network. So like thinking like wiring a couple computers together to play Counter-Strike, which IT people we really want to do that at some point. The internet layer provides internetworking between independent networks. So this would be like connecting to another network at maybe another school or something like that. Transport layer handles host-to-host communications. So like all of the TCP and UDP, which we'll talk about in a minute, goes over the transport layer. And then the application layer is like what application engineers work in most of the time, which is things like SFTP, HTTP, HTTPS, stuff like that. So some examples, we have ARP, which is Address Resolution Protocol. I'm not going to talk about this today, but this would be like MAC address stuff. Obviously, IP is at the internet layer, TCP and UDP at the transport layer. and then HTTP, things like that at the application layer. So this is kind of sort of like a vertical breakdown of like what a packet really looks like. We have a header and a footer, obviously, to tell us, when it starts and when it ends. On top of that, we have the IP data, and then on top of the IP data, we have UDP in this example, but it could also be TCP or something like that. And then the actual data is sort of the tip of the pyramid. So you can see there's actually a lot of overhead for sending, communication over the internet. There's also a lot of different ways to send communication over the internet. Right here, we have a ton of application layer protocols, transport layer protocols, mostly TCP, UDP. Google invented one called Quick, which is supposed to be a little bit better, but I don't know, it's Google stuff, so whatever. Internet layer is like IP, and then the link layer is a lot of the low-level stuff. We're going to talk mostly about these three today. So IP, like I said before, is the primary protocol in the Internet Protocol Suite. It was named after it. It's responsible for delivering packets from source to destination, regardless of the network boundaries. So think of it like a package. It kind of has a to address and a return address, right? And the protocol is going to be responsible for getting that there. The routing function is essentially the biggest, it's the backbone of the internet. And all of your computers, right, if you go to the sysprefs, you can actually see what IP addresses you have. The fastest way to show an example of all this routing in action is actually just using traceroute. So if you ever fire up your terminal and you can traceroute to another server on the internet, it's going to show you each and every hop, that each and every router that your packets touch in between you and the destination. So I tried to distill this down into some meme formats so that it's easily digestible. But basically, our sweet computers are yo, can I talk to 8888? And then the Cisco router upstairs in the closet's yeah, I don't know how to get there exactly, but I can ask my gateway. So then Cisco's hey, my buddy wants to get here. Do you know how to get there? And then Time Warner's oh yeah, I don't really know exactly either, but I know that I have another gateway that can maybe tell me. So each one of those rage faces, right, is going to be a different hop in the in the actual trace route. So like I said before, IP is kind of the delivery truck of the internet. It actually doesn't care what kind of data that it's sending. It could be TCP, it could be whatever, it could be encrypted, whatever. It basically has the return address on each box and the address to which it's going. So a little bit about TCP. TCP is the transport layer protocol that sits on top of IP. This is connection oriented, meaning that the session actually has to start before data can be sent, because not every packet in a TCP stream is going to have all the source and destination information on it. The good thing about TCP though is that it's reliable. It's ordered, so you can send data, it can get corrupted, and then put back together on the other side, and it's error corrected. So this is the TCP state diagram. I really have no idea what's going on here. I tried to distill it again, but you'll notice a lot of SYN and ACKs. And if anyone's a Mars Attack fan, it's it actually stands for acknowledge. So it's basically after you get a message, you're you as the receiver acknowledge that you received it. So I wanted to do a stupid example of TCP with stupid bros, because one time I heard a conversation and then randomly later, because I'm a nerd, I was it sounded a lot like a TCP SYN-ACK setup. So I'm trademarking this, don't anybody steal it. But so to start, the client A is yo, bro. And then the other guy's yeah, bro. And then the next guy's can I ask you a question? And then he's sure. And then they actually send the message, and the client responds with the answer. And then the original person's okay, cool, I'm done talking to you. And then the last person's cool, I'm done too. So that was TCP in a nutshell with pros. So last is UDP. UDP is it also sits on top of IP. It's connectionless, meaning packets are delivered or not without the source host knowing. It's kind of like fire and forget. It's very unreliable, unordered, and it's not error corrected. So you might be thinking well, why would I want to use this if it's kind of junk? But it's super, super fast. It's super lightweight. So mostly UDP is used for things like streaming video online or gaming or something like that, which gamers in the audience might be oh, well, that's why I lag. And it's well, yeah, because sometimes you or the other people you're playing with might be actually dropping packets, so that when you go to fire or kick or whatever, it's a little bit lag. An example of UDP in real life, this has happened to me a million times, maybe other people as well. a parent or someone asks you, can you take out the trash? And you just pretend not to hear it. But the parent doesn't care if you heard it or not. They're going to keep trying to send the message again. Can you take out the trash? Can you take out the trash? And then I eventually have to take out the trash. But the coolest part about all this, like if you care about the geeky details of these protocols, all of the original RFCs are published online, and you can read like some really crazy stuff written in like the 70s and 80s that describes these protocols exactly. There's one for IP, and then this one actually includes a little sweet ASCII diagram. So that's all I got. It's web surfing time. But thank you, everybody.